An AI sees the word cat as a point in 1024 dimensional space, and kitten sits right next to it. That's how it knows what words mean. Let's ignore 1000 dimensions for a moment. Imagine instead a simple two dimensional map. Words are points on this map. Similar words sit close together. Unrelated words sit far apart. Drop the words cat, kitten, dog, car, truck, bread, and pizza onto this map. Three clusters appear all by themselves, which are animals, vehicles, and food. Nobody told the AI what those categories were. The corresponding geometry just emerged. Real embeddings aren't two dimensional, they live in 768 or 1024 or even 4096 dimensions. Each word becomes a long list of numbers. More dimensions means more nuance. Cat and kitten share most dimensions but differ on the one that can capture, for example, age. Cat and tiger share the dimension for feline but differ on the one for wild. Each dimension is a tiny axis of meaning. You can't draw 1000 dimensions, but you can compress them using techniques called TSNE or UMAP. They squish the high dimensional cloud down to two dimensions you can finally see. Information is lost in a bit, but the structure remains. So, how do we measure how close two words are inside this space? The answer is cosine similarity. It looks at the angle between two arrows pointing out from the origin, and the intuition is straightforward. Two arrows pointing in the same directions are aligned, means very similar. Two arrows at 90 degrees are perpendicular, which means basically unrelated. And two arrows pointing in opposite direction means opposite in meaning. Cosine similarity is always a number between -1 and 1. 1 means identical direction, 0 means unrelated, -1 means complete opposites. That single number tells the AI how related two ideas are. Let's take two sentences. I love pizza and pizza is my favorite food. They have cosine similarity of around zero point 0.9. The same sentence compared with my car is broken scores only around zero point 0.1. Same words don't matter, only meaning does. And now, an important part, which is the key essence for embeddings. So, embeddings encode relationships directly in their geometry. The vector for king minus the vector for man plus the vector for woman is almost exactly equal to the vector for queen. And this math actually works. And why does this work? Because the embedding was trained on billions of sentences. The model noticed that king relates to queen the same way that man relates to woman. That relationship became a fixed direction in space, which is the royalty direction or the gender direction. And it's not just one analogy. Paris is to France as Tokyo is to Japan. Walking is to walked as running is to ran. All of these analogies show up in the same parallelogram drawn at different places in the space. How are embeddings actually trained? The classic way is predict the surrounding words. If cat keeps showing up near meow or fur, the training nudges their vectors closer together. After billions of examples, related words simply end up nearby. The modern way is contrastive learning. Show the model two sentences that mean the same thing, pull their vectors together. Show it two unrelated sentences and push them apart. Over millions of examples, meanings get baked into geometry. Today's best embedding models, such as OpenAI's Text Embedding 3 or Cohere's Embedding V3, they output sentence level embeddings, not just word level. A whole paragraph can become a single point in space. But how does a sentence actually become a single vector? First, it's split into tokens. Each token starts as a row pulled from a learned lookup table. A transformer then mixes them together with self attention, so every token absorbs its context. Finally, all the token vectors are averaged into one single point that captures the whole meaning. There can be several use cases. So, use case one is semantic search. So old search matched keywords, new search matches meaning. The query, how do I cancel my subscription, will find a help article titled End Your Membership Today, even with zero keywords in common. Use case 2 is RAG, or Retrieval Augmented Generation. Embed your whole knowledge base, embed the user's question, pull the closest matching documents, hand them to an LLM, and that's the dominant pattern behind every AI assistant that knows your private data. Use case 3 is clustering. Embed thousands of documents, group the ones that sit close together. The clusters that emerge often correspond to real topics without anyone labeling a single document by hand. Use case 4 is classification. So train a tiny classifier on top of the embeddings. With just a few hundred examples, you can do sentiment, topic, or intent detection, far cheaper than fine tuning the whole model. But there is a trade off. More dimensions means richer representation, but more compute and more storage. Most production systems land somewhere between 512 and 1536 dimensions, which is the sweet spot. Embeddings turn meanings into math problem you can solve with linear algebra. They are the quiet foundation under search, RAG, recommendations, and classification. Almost everything practical built with LLMs.